Thanks to Scott. Thanks, Scott, for the introduction. This is joint work with Nadesh and with Alex Wolfowski. So let's consider a basic problem of estimating the average treatment effect from a group of units. A typical assumption in causal inference is the stable unit treatment value assumption, which requires that treating one unit doesn't affect other units. When this assumption fails, so for example, if there's interference between units, standard experimental designs and estimators are biased and sometimes even inconsistent. When the units of treatment are the nodes in a network, it's natural that there's interference. So for example, if the nodes of treatment are people, and the network is Facebook, well, treating me may very well affect some of my friends. What we do in this paper is to take a design-based approach to causal inference in networks with interference. And what we're going to do is, what I'm going to present is a new class of experimental designs that yield, under certain assumptions and sufficiently large graphs, yield unbiased estimates of the average treatment effect. So the outline of this talk is as follows. I'll start out by describing the basic framework for modeling interference in networks. I'll then explain how experimental design can help reduce bias of standard estimators. I'll then describe our new experimental design and prove some bounds on mean squared error. And I'll conclude by comparing our experimental design to standard ones in simulations. So the framework is as follows. We have a finite graph, and I'll assume always that there are no isolated nodes in it. And the nodes are the units of treatment. Interference occurs along edges. And I'll assume that there are r times n vertices in the graph, and we'd like to treat p times n of them. So the ratio between p and r is the fraction of nodes that we want to treat. And I'll denote by n of v the neighborhood of a vertex v. Yeah. Yeah. So the under stable unit treatment variance value assumption, observations take the following form. What we observe is a covariate, xv, plus some treatment effect. So if a vertex is treated, I'll let t be the set of treated vertices. So for treated vertices, there's an additional term in the observed value, which is the treatment effect, tv. And for untreated vertices, this term just vanishes. What we do is we consider a model where there's an additional term corresponding to interference. So I'll let f of ab denote the interference effect that a node experiences if a of its neighbors are treated and b of its neighbors are not treated. So then the observation gains an extra term, which is f applied to the number of treated neighbors of v and the number of untreated neighbors of v. Now, this specification of the model has some implicit assumptions. So I'll highlight two of them. One of them is I'm assuming additive separability between the interference effect and the direct treatment effect. So conceptually, the assumption is that treating a vertex doesn't affect how it experiences interference. And this assumption is absolutely crucial to our analysis. The second assumption is that the interference effects only depend on the numbers of neighbors that are treated. So the implicit assumption is that all neighbors affect a node symmetrically. And that second assumption is not as important, but I'm just making it for sake of simplicity. Well, I want to give a couple of examples of what this interference function can look like, the simplest examples. The most basic example is a linear interference function. So f of ab is gamma times a. What this means is that every treated neighbor adds gamma to the observation. Another example would be a linear interference function with a threshold, so where only the first k treated neighbors affect cause interference. So that's f of ab is gamma times the min of a and k. So only the first k treated neighbors count. A different example is a proportional interference model, where instead of thinking that high-degree nodes can experience a lot of interference, think that, well, interference depends on the proportion of neighbors that are treated. That also falls into our framework. This is f of AB is gamma times the fraction of treated neighbors. The fraction of treated neighbors is A over A plus B. These are just some examples to keep in mind. The estimand that we consider is the average treatment effect. So it's the average direct treatment effect. So that's the average of these TVs over all the nodes. And we always use the Neymanian estimator, which is the difference between the average observed value of treated vertices and the average observed value of untreated vertices. Recall that YV is the observation. And the design problem is to choose an experimental design, which is a distribution of the treatment group T, to make the difference between the estimator and the estimand small in probability. To focus on interference, I'm going to kind of only consider the contribution of interference to the estimator. So imagine an alternate reality in which world is the same except there's no interference. Then what the Neymanian estimator would be is some idealized version, where basically there's no interference terms. So for treated vertices, the observation is just the covariate plus the treatment effect. And for untreated vertices, we just observe the covariate. And now we're back to a classical environment. And one of the nice properties of the Neymanian estimator is that if you treat every vertex with probability half, then I think that shouldn't be half. It should be, let me not worry about this right now. Basically, if you treat nodes with the appropriate probabilities, then this is an unbiased estimator. So what I'll focus on is the difference between the Neymanian estimator and this idealized version. So keep in mind, we can't observe this idealized version because of the interference effects. So the difference I'll denote by xi. And what this is, it's the average interference effect on treated nodes minus the average interference effect on untreated nodes. And in the talk, I'm just going to focus on making this quantity small in probability. In the paper, we actually focus on making the estimator itself close to the estimand. So let me give you an example of how choosing a design appropriately can help make this net interference effect small. So consider a square. That's the graph. There's 4 vertices arranged in a square. There's essentially 2 kinds of ways you can treat 2 nodes. One is you can treat adjacent nodes. The other one is you can treat diagonal nodes. And I want to make a case that these 2 are actually fairly different from one another from the perspective of interference. So actually, the adjacent one is going to turn out to be better. And here's why. So if you treat 2 adjacent vertices, so say the red ones are the treated, red nodes are the treated ones, then what happens? Every vertex neighbors 1 treated node and 1 untreated node. Right? For example, the top left node has a treated and an untreated neighbor. So that means all nodes experience the same interference effect, namely f of 1, 1. In particular, this means that the interference effects on treated and untreated nodes cancel. So f of 1, 1 is both the average interference effect experienced by treated nodes and the average interference effect experienced by untreated nodes. So this net interference effect is 0. On the other hand, if we treat 2 diagonally opposite nodes, then what happens? Treated nodes have only untreated neighbors, while untreated nodes have treated neighbors. And that's a problem, because this means that the average interference effect experienced by treated nodes is f of 0, 2, while the average interference effect experienced by untreated nodes is f of 2, 0. And that difference is not going to be 0 in general. So the strategy that we take in this paper is to restrict the randomization in the choice of treatment group to ensure some kind of balance, basically to try to stay in situations that look like treatment of adjacent nodes and don't look like treatment of diagonal nodes. So I want to be a little bit more precise about what I mean by this notion of balance. So I'm just going to spend a few minutes about giving a classification of simple class of designs for which interference effects vanish. So I'm going to consider, let's assume for right now that the target treatment fraction is half. So the ratio P over R is half. One kind of simple design you can do is you split the nodes into two groups of equal size, and you just treat one of the groups. So formally, I call a quasi-coloring a set of vertices that consists of half the nodes. And the design is, I'll denote by TS, and this means that you treat S with probability half, and you treat the complement of S with probability half. And well, if you treat S, then essentially the thing that one cares about is the number of neighbors that every node has that are in S, and the number of neighbors that every node has that are not in S. And so I'll call that the bi-degree of a node V. So formally, the bi-degree of node V is the pair of the number of neighbors of V that are in S and the number of neighbors of V that are not in S. And we don't really care about vertices on their own. We just care about the overall distribution of this among both the treated and untreated nodes. So I'll form this distribution. I call it ds. It's the net bi-degree distribution. What it is it's the difference between the distribution of bi-degrees of members of S and the distribution of bi-degrees of members of the complement of S. So in terms of the notation, this is just the average. It's a sum of delta masses at the bi-degrees of all members of S, and minus a sum of delta masses at nodes that are not in S. And the point of this distribution is it's closely related to the net interference effect. So basically, the net interference effect is going to be the integral of interference function against this distribution. So why is that? I mean, what's the interference effect? It's the net interference effect. It's the average interference effect on members. The net interference effect, if S is treated, is the average interference effect on S minus the average interference effect on S complement. But what's the average interference effect on S? It's basically the integral of F against the distribution of bi-degrees of members of S. And the average interference effect on S complement is the integral of F against the distribution of bi-degrees on S complement. And so this means that the net interference effect is actually the integral of F against this net bi-degree distribution. So what does that tell us? That tells us that the net interference effect vanishes if and only if this net bi-degree distribution vanishes. So that's what I mean precisely by balance. It means that the distributions of bi-degrees of the treated and untreated vertices should coincide. Now, it would be very nice if we could always find some kind of balanced treatment design. But unfortunately, that's not always possible. So here's an example. Consider a graph with two vertices, one edge. This is like the simplest non-trivial graph. And let's suppose that there is some non-trivial interference. So f of 1, 0 is gamma. F of 0, 1 is 0. This is a linear model where treating a neighbor adds gamma to the observation on a vertex. And suppose that exactly one node is treated, which is kind of the only treatment design you could imagine in this graph. I claim that the net interference effect is always minus gamma. And why is that? Well, the treated node will not have any treated neighbors, and so it won't experience any interference, while the untreated node will have a treated neighbor, and therefore will experience interference gamma. So that means overall, the amount of interference that we see is minus gamma. It's the difference between the treated node's interference and the untreated node's interference. And so in particular, bias cannot be eliminated by choosing the treatment design. So the point of the paper, the remainder of the paper, is that we show that asymptotically, there's no bias of this form. It's not going to be true in small graphs, but in large graphs, we can approximately eliminate bias. And the design that we use is a stratified design. where we stratify nodes by degree. So the idea of the design is as follows. First, we take all the nodes, and we start by forming some large strata. And those strata should have size divisible by r. Recall that p over r was the fraction of nodes that we wanted to treat. So we're going to form strata that are size divisible by r and that consist of nodes of just 1 degree. So in fact, there may be no such strata if the degrees of vertices are quite different. But let's not worry about that. So there'll be some vertices left. And there won't be too many of them of any given degree. And then the second step is to divide these remaining vertices into some strata of size exactly r, and of degrees that are as similar as possible. And then we treat p over r fraction of the nodes in each strata. So what's the basic idea? We want to stratify so that each stratum consists of nodes of similar degree. And if possible, these strata should be large, but sometimes that might not be possible. So let me be a little bit more formal about each of these 3 steps. So to form the large strata, what I do is the following. We let vk be the set of degree k nodes, and the stratum is going to be some subset v prime k. And that should have size divisible by r, and this v prime k should be essentially as big as possible. So it should miss at most r vertices. So it's a set of v prime k is a set of nodes of degree k that has size divisible by r and is as big as possible among such choices. So that's the first kind. Those are the large strata. And there's going to be some remaining nodes. And I assume that the number of nodes in the graph is divisible by r. So the number of remaining nodes is also divisible by r. So say the remaining nodes are w1 to wrk, and order them in decreasing order of degree. And then to form these strata of size r, what we do is we take the r highest degreed vertices and combine those into a stratum, which I call v double prime 1. Then take the next r highest degreed vertices. That becomes v double prime 2, and keep on doing this. So we're forming groups of r vertices that are of as similar degrees as possible. And then we treat p over r nodes in each stratum. So formally, the stratification is a partition. It's these v primes, which are the large strata, and these v double primes, which are the strata of size r. And the treatment is TP, which is uniformly random among all choices of treatment, a treatment group that treat p over r fraction of vertices in each component of the partition. So we're not going to ensure exact balance. So that net bidegree distribution is not going to be identically 0. And so we're not going to be able to exactly cancel interference effects, but we need to make sure that interference effects are approximately going to cancel. So the way that we ensure this is to ensure that vertices with similar bidegrees experience similar interference effects. So that's some kind of continuity condition on the interference function. We basically need to make sure that if a and b don't change too much, then f doesn't change too much. The way that we do this formally is we require that f is Lipschitz with respect to a particular metric. And the metric is defined as follows. Fix 2 constants, k1 and k2. And the metric, it's actually a pseudometric. The distance between a, b, and cd, recall that a and c are numbers of treated neighbors, and b and d are numbers of untreated neighbors, is the following. It's k1 divided by d max times a plus b minus c minus d, absolute value. And so what's a plus b? That's basically the degree. It's a degree of a vertex. C plus d is also a degree of the vertex. So this first term is k1 over d max times a difference in degrees, where here d max is the maximum degree in the graph. That's one term. And the second term is k2 times difference in treatment fractions of neighbors that are treated. So a over a plus b is the fraction of neighbors of some vertex that are treated. And c over c plus d is the fraction of neighbors of some other vertex that are treated. And the second term in this distance function is k2 times the absolute value of the difference. And what we require is that f is Lipschitz with respect to this metric. So conceptually, what's that saying? We're saying that interference effects can depend on both the degree of a node that's experiencing interference, as well as the proportion of its neighbors that are treated, but it shouldn't really depend too much on either. So for suitable choices of these constants k1 and k2, these linear and proportional interference models are going to satisfy a Lipschitz continuity condition with respect to a metric of this type. Again, what this is really just saying is that at changing treatments of a few neighbors can't really affect interference effects that a vertex experiences too much. So I'm going to now give two results about how our designs can eliminate interference. One's kind of going to be applicable in dense graphs, and the other one in sparse graphs. We haven't really made any parametric assumptions on the graph. So let me start with the dense case. So let d min be the minimum degree of nodes in the graph. And the result is that if the interference function is Lipschitz, in the sense I just described, then this net treatment effect is at most is on the order of 1 over d min at most in expectation. And the expectation of the square of the net interference effect is also on the order of 1 over the min degree for the treatment design, the stratified design that I described. And the implied constants depend on, not on the graph, but on the other parameters of the model. So they depend on these constants k1 and k2, and they depend on the target treatment fraction. So let me give some interpretation first of what these two quantities are, this expectation and the expectation of the square. Essentially, the expectation of the xi is the amount that interference contributes to the bias of the Neymanian estimator, while the expectation of the square of xi is the amount that interference contributes to the mean square error of the Neymanian estimator. So what this result says is basically the contributions of interference to bias and mean squared error are at most 1 over the min degree of the graph for our treatment design. So in particular, if the min degree in the graph goes to infinity, then this net interference effect is going to go to 0 in probability for our design. And moreover, if the min degree grows at least linearly in n, then the effects of interference on bias and mean squared error are going to be on the order of 1 over n. And keep in mind that 1 over n is just the order of the bias and mean squared error of the Neymanian estimator even without interference. And so this is saying that when the min degree grows linearly, interference doesn't contribute more to error than there is error already. The assumption that min degree grows quickly is a bit restrictive. So in sparse graphs, one doesn't expect this assumption to be true. And the second result deals with sparse graphs. The result is that if the same Lipschitz continuity condition is satisfied, what we show is that the expectation of xi is on the order of the difference between the max and min degrees in the graph divided by n. N is basically the size of the graph. And the expectation of the square of xi is on the order of the square of the max degree divided by n times the min degree. And again, implied constants don't depend on the graph, but depend on the other parameters. So what does this imply? Suppose that the max degree is strictly smaller order than square root n. Then what this implies, if you look at the expectation of the square of xi, the numerator is at most n, the denominator is at least n, and so this thing goes to 0. And so what that tells us is that the net interference effect goes to 0 in probability, as long as the max degree doesn't grow too quickly. And if, furthermore, the max degree is bounded, then the effects of interference on bias and mean squared error are on the order of 1 over n, which is the underlying error of the Neymanian estimator anyways. So these two results are applicable in very different regimes. Basically, what the first result is that if the min degree grows, interference doesn't affect our designs too much. The second result is that if the max degree stays bounded, interference still doesn't affect our design too much. I mean, there are other regimes, but at least in these two regimes, our design is able to deal with interference. So let me give some ideas behind the proofs of these two results. I'm going to focus on the mean square error bound because I think that's the more interesting one. And the idea is the following. Well, first thing is there's a lot of randomness in the design. What we do is we first decompose that randomness into some pieces and then show some kind of approximate balance in each of these pieces. So let me be a little bit more precise about what these pieces are first. So recall there's this stratification P that I defined to define the design. I'll choose a random refinement P prime as follows. So P prime should consist of, it should be a partition of nodes into groups of size R, and it should be a uniformly random refinement of P, of the partition P. So basically what we're doing is there's some of these large strata, and we break them up randomly into groups of size R and keep the small strata the same. And the point is, because of the uniformity of everything, we could instead treat P prime as the stratification. P prime, keep in mind, is random, but using P prime as a stratification is the same as using P as a stratification in the sense that you get the same distributions of treatment groups. And so these are the idea of breaking up the randomness into pieces is the following. Let the components of P prime be P prime 1 up to P prime n. So these are some disjoint subsets of disjoint sets of nodes, and each of them has size R. Then the sets of vertices in P prime 1 that are treated, and basically if you look at the treated vertices in each of these parts, those are some sets of nodes, and they're random, and they're conditionally independent given the partition P prime. So those are kind of the individual pieces of randomness involved in our design, and I'll kind of breaking up the randomness is going to help to simplify the structure of this treatment design. And then the idea is basically to show that there's some kind of approximate balance within each of these groups P prime I. So, I mean, I earlier only defined this net bi-degree distribution in the case in which the target treatment fraction was 1/2. But you can also define it for general target treatment fraction. So this is exactly the same definition. You'll take the difference between the bi-degree distribution of treated vertices and the bi-degree distribution of untreated vertices. So that's dt. I'll let dit be the contribution of nodes in the set P prime I to this net bi-degree distribution. And if we condition on both the partition P prime and the set of vertices in P prime I that are treated, then, well, what's going on? We have some vertices. We have R vertices. Some of them are treated, some of them are not treated. And what's going on outside is just essentially random. There's not too much dependence in the treatments of what's going on outside. And that means basically, well, the key is that vertices in P prime I all have similar degree. And because the binomial distribution is concentrated, this means that essentially all the vertices in P prime I will have similar numbers of treated and untreated neighbors. And so that gives a kind of balance. And so once we remove the conditioning, we get a bound on this dti. So I should specify what I mean by bound on dti. This is a distribution. I fixed this metric d. And the bound is really on the Wasserstein norm of that distribution. Because what we're saying is that this distribution is close to 0, but it's in the Wasserstein sense. So now, to finish the argument for these MSE bounds, you have to break up into two cases, the dense and sparse cases. And the arguments are going to be somewhat different. But the point is, recall that the net interference effect is the integral of the interference function against this net bi-degree distribution. So in particular, absolute value of the interference effect is absolute value of the integral of the interference function against the bi-degree distribution. But well, f was required to be a Lipschitz function. So by the definition of this Wasserstein distance, that means that this integral is bounded above by the Wasserstein norm of the net bi-degree distribution. So now we can combine this inequality with the bound I just discussed. The way we combine it, the way we relate these two is via some triangle inequalities. So we need to use two of them, one for the Wasserstein distance and one for L2. So the idea is, well, if you take the expectation of the square of xi, is bounded above by the expectation of the square of this Wasserstein norm of the bi-degree distribution. And then, well, you can break up this Wasserstein norm into pieces based on the contributions of each of the sets P prime I. Once we break it up, well, we end up with a sum. We end up with a square of a sum. And the L2 triangle inequality lets us convert that into a sum of squares. And then to conclude, well, now we have a bound on this expectation of the square of xi in terms of the expectations of the squares of these Wasserstein norms. And we have bounds on those, and that gives a bound on this mean square error term. So that's the case of dense graphs. For sparse graphs, it turns out that this L2 triangle inequality is just too weak. And why is that? Well, the L2 triangle inequality allows arbitrary correlations between these distributions DIT. And there can only be correlations between them when there are enough edges in the graph. And in sparse graphs, there aren't that many edges. So there's some kind of independence between many of these. And we can leverage that a bit to help us. So let me skip the details and go to some simulation results. So the first class of graphs we consider for simulation. So I should say the simulations compare our design to a completely random design where you just treat you uniformly choose a treatment group. Simplest class of graphs one can consider is error-Schrödinger graphs. So we consider a linear interference model with normally distributed covariates and normally distributed treatment group. And x's are going to be, we plot log mean squared error against this parameter gamma. So gamma measures how much interference there is. Consider two randomizations. One is ours, and the other one is the completely random design. Basically, the performance is similar. And in some cases, the completely random design even slightly outperforms our design. Why is that? That's basically because the completely random design has more randomness. And in the homogeneous graph, stratifying by degree is not going to help you at all, because all the vertices are basically the same. So conclusion is that completely random design can slightly outperform our design in homogeneous graphs. But our design is not doing that badly. Like, the difference is pretty small. So to illustrate some of the advantages of our design, I'll consider a different class of graphs, which are inhomogeneous. So these are so-called preferential attachment graphs. And the idea is that it's a model of graphs that's defined sequentially. And when you add a new node, it's more likely to form connections with nodes that already have high degree. So formally, when we add a new node W, a new node V, it forms M edges, and it connects to an existing node W with probability proportional to the degree of W raised to some power parameter pow. And these graphs are pretty inhomogeneous when the power parameter is large. So, I mean, that's because when the power parameter is large, there's high correlations between edge formations. And what happens to the performance of our design is quite different in inhomogeneous graphs. So again, we work with the linear interference model and normally distributed covariates and treatment values. And we consider two values of this number of edges that are formed each step, 4 and 6. And basically, if you look, for example, at these bottom two figures, our design outperforms the completely random design. Basically, because we're able to exploit the fact that vertices are different, and the difference between vertices is captured in terms of their degree. And that's precisely the kind of variation that our design exploits. And when m is equal to 4 and the power parameter is 4, something dramatic happens, which is that the mean squared error is unaffected by the amount of interference for our design. And why is that? That basically tells us that our design is perfectly canceling interference in these graphs. And the reason is when m is small and the power parameter is large, the graph has a really tight structure. And our design is perfectly exploiting that, essentially. So the conclusion is that our stratification design can substantially outperform a completely random design when the graph is inhomogeneous. In the paper, we do some other things. So first, instead of proving bounds just on this net interference effect, we prove bounds on the mean squared error of the Neymanian estimator itself. And we also relax the assumption that vertices are symmetric. Basically, we allow there to be multiple types of vertices and interference to be type dependent. Instead of stratifying just based on degree, you also stratify vertices based on type. And we show that similar results go through. So to conclude, what did we do? We formulated a model of causal inference in networks, and we illustrated how balancing the treated and untreated nodes can help to reduce bias and mean squared error. And we also designed a stratified sampling method and proved theoretical guarantees on how this sampling method performs in settings with interference. And thank you all for listening.
Questions?
Yes?
Have you thought about extending this to degree edge weights that aren't one, or degrees of the edge weight?
Yeah, we've thought about it a bit, but have not done anything. I expect that a similar kind of argument will go through.